Here we are. We are record. All right.
All right.
Yeah.
Hello?
Yes, we can
Hi.
hear
Hey,
you.
Jefferson.
Hello. I'm finally here.
Yeah. Yeah.
I thought we didn't have meeting when I was in Singapore,
Mhm.
and yeah, but it was, and then I forgot last week. It was really bad, but
No, it's fine. Enjoy your break. Summer.
I
yeah.
once forgot. I once forgot to start my own meeting. I'm usually the one that hosts these. I forgot one time.
Oh, yeah. So what are we doing?
Oh yeah, just presenting something. Ethan, do you have anything to present? Or just
Okay. I just have updates on what I've been working on.
Mhm.
If you want to see. Okay. Let me see if I can share my screen. No, I'm just gonna share my whole screen. I got nothing to hide. Hold on. That came out weird. Hold on.
What do you mean? You're gonna hide?
Hold on. It's giving me problems. It's like asking me to do advanced settings. Oh, never mind.
Turning off some window. There you go.
All right. Is everything visible?
Yep.
Mhm.
Okay, so I'm going to first talk about what I found. So this is the thing I'm most worried about is the data set I found. So it has in total about 1,700 compositions. These are for multi-principal holding gosh, what's the correct word for these? Like multi-component principal alloys or something like that?
High entropy alloy, or I don't know.
Well, high entropy alloys are a form of them that have very similar compositions. But in theory, if anything has more than like two compositions, it's a multi-principal. Uh,
Principal elements alloy.
yeah.
Yeah.
So apparently, according to the paper that introduced this, that I found this from, this is the largest data set available for them. But the problem is that even though it has 1,700 compositions, many of the files for certain properties are empty. So
Hmm.
the one I've been working with the most, which is compressive strength, only has 490 entries. There might be some that have more. Um, that is the thing I'm most worried about. But I think again, like what I'm more trying to aim for with my model is getting better than average results because I know that my model isn't actually modeling something. And since this isn't the state of the art issue, I'm not entirely super worried about it, although Cal might be concerned. I'll bring this up when we meet on Monday. Um, so yeah, that's all I have to say about this. Do you have any questions? It has a lot. There's actually a lot of components. There's like I think 20 or something um, different elements in here.
How
Have you made
many?
like a? I
Yeah, go
can
ahead.
go.
You have to visit.
Okay, I was like, I was wondering if you have made like a distribution graph, because that's what when you're doing like when you first get data, usually can put like certain columns into like graph and see the distribution, especially for like the composition with 400. Like I was wondering like what's its histogram like, because it might be only certain range of values, and or it's just like one value. Like, have you done like
Yeah,
a histogram of it or
I
anything
I
like that?
haven't. What I have done is okay, so it takes me about an hour to really you're seeing my model right here, right?
Mm-hmm.
So see with these values, so this value right here, this is the total loss, this is the error loss, and this is the Wasserstein loss. And I made my error function so that it always starts at 1. Um, hold on. So the thing is, this has so many values, it's not showing them all. But whenever it starts, it always starts at 1. And this helps the loss function not when I'm giving it loading steps, like the step size. This is so it's always about the same, no matter what sort of data set I load. Um, so this thing can get somewhat low, but it doesn't do everything I want it to yet. I think I might actually have to add more layers. It might not be modeling properly. But I'll just run it for let's see. Let's just run it for just 50 rounds. Because I do have one sort of graph. Hold on, maybe taking a while. What I initially do is I try to plot the properties it has of any given thing I'm aiming for, and then inside the latent space, how far it is from the center of the hypersphere that I'm trying to map it onto. And so far, I actually haven't gotten it to create a good linear relationship, which is necessary. So my model isn't great yet, but this does actually show the distribution of the different properties it has. So you'll see pretty soon. Once it finishes training, and it shouldn't take too long. So this is far from ideal. Ideally, this should be like a straight line where like the points right here to cluster near it should form like a line right like this, a linear relationship between the properties and the distance, but that isn't what it did yet. However, okay, so I'm trying to figure out how to word this. So this is compressive strength, I think in megapascals, and so you can see that. Just ignore this dimension right here. It's kind of irrelevant. If you're asking about the distribution of properties, Jefferson, you can see most of them cluster around like 1500 megapascals, I think.
Mhm.
But yeah, there's quite a wide range actually.
Well, can you delete like those two outliers? There's like two outliers at top, and then maybe like the scale will be different. I'm not sure. Or
No, this hasn't had a long enough time to train. It literally takes an
oh,
hour for this to train, and I haven't been able to get what I want it to do yet. Like I was saying, I think I'm gonna have to add more layers. It might not be being able, it might not have as many degrees of freedom as it needs to model it properly.
do you have the
Um,
graph of what it looks like after an hour? Like, is it closer to like the line you mentioned?
it's sort of there. It's not good enough. Like it really is not even like slightly. Like I can almost see it, but it does say that the Washington distance is lower than when it started. Which is a good sign, but it just isn't enough really to make a difference.
Hmm.
Like it is training, it is learning. It's just not doing what I want it to.
Is this
That's
something that is due to this data frame, like this data set, or
What?
is this something? Is this like a problem with this data set that caused it to be not be like ideal?
I don't think so. I think if I had a smaller data set, it might actually learn faster. But it might not learn the right way.
Like,
Because
I was wondering. Yeah.
I had the same issue with random data though. It was kind of forming a line, but it wasn't very good.
Yeah, I was wondering if you could perform because you build a model, right? I was wondering if you could perform it on like another data set, like actual data set from um Kaggle or something like that. And then you can
Kaggle. What's that?
um it's like a website where you can get data set. Let me send it in chat. Like I use
Okay,
it
I'll
to
look at
get
it.
image recognition, but I'm not sure. You can probably get, yeah, you can get a lot of free data set from here.
I'm not
Um
working with images, and I don't think it would work.
it's not
Um,
image. There's different types of data set that you can just take and borrow. It's like
okay,
data.
cool.
It's
It
like
might have what I need.
mhm. Yeah, it has like data. I'm pretty sure it has data set that's like your format.
Yeah, I'm working
Which
with
has,
Excel.
yeah.
Okay, let me just make sure I click on your link. Okay, hold on.
put it in the resource channel too. So
Okay, good. Now I have a tab
Yeah.
opening up. Okay, what okay, yeah, it kind of had the same issue with random numbers. I actually tested it too on the TEC data set, which oddly enough might actually be larger than the one I have, due to the fact that it has like 718 entries. Um, and it sort of formed a line with that one too. Okay, hold on. Let me show you else what my model is able to do. So okay, so in addition to this, it will plot the error over time. Wait, it's not showing it. isn't very organized. Sorry about this. Oh, here it is. Here we go. So it didn't have very much time to learn, but as you can see, the error did go down. And then the same happened with Wasserstein distance. Hold on, let it learn. Load. So yeah, and it's actually quite smooth usually. It does seem to be learning quite smoothly, but it just isn't getting to the point where I need it.
Only 50 epic though.
All right.
50.
Any questions?
Let's see.
What'd you say?
It's only 50 epic though. Like the amount of training is not that much.
Yeah, I had to run it for like an hour or 30 minutes for it to really show big effects.
You use GPU or just CPU?
Oh, I just run it on this computer.
Then it's probably a CPU, but you don't convert it to a GPU. Very slow.
Yeah. You use Google Colab, right?
I'm using my GPU right now actually.
Wait, so okay, so this is a PC-10. Does it have a GPU or is it something I would add on?
I have no idea. You have to check. With
Okay.
the hard rock, I have no idea about that.
Okay,
Oh,
isn't the
Triet,
Yes.
have you ever used like a server to run?
You mean like Google Colab?
Yeah, it's like, do you have to pay for that? I mean, how
No,
much do you have to pay for it?
we don't pay for Google Colab. It's free up to I think 12 hours
Oh,
of
yeah.
GPU. Yeah.
Huh, okay.
But wait, so CUDA, I know a little bit about that. Is that a function that like will let you delegate tasks to certain GPUs?
So for CUDA, you can you have to go back to NVIDIA. So it's a hardware company that produce GPU, and then CUDA is kind of the software in between that you can use NVIDIA GPU to connect to machine learning.
Okay. I think I'll probably just make sure I get my model made all set up first before I try doing stuff like this because I don't have only have like 2 weeks left before the school year starts.
Yeah. You can try on Google Colab too, maybe faster.
How would that work? Would I just would I just paste everything I have here onto there?
Yeah, maybe you have to twist here and there, but yeah, mostly like that. Yeah.
Okay. Yeah, I'll just keep changing my network or playing around with it tomorrow. Do you have any questions?
No, not really. Yeah, it's good.
Yeah.
The problem is
Oh,
mainly
this
just uh the amount of data, right?
yeah, when we meet with him on Monday, I'll ask Professor about this. Um, oh, this, by the way, when I was building this is the hardest part was loading the data because it was like it was
Um,
it had all these issues because like the data set wasn't compatible with like the neural network and stuff like that. I just remember this being really time consuming.
you use ChatGPT.
ChatGPT. No, I don't.
You should use
Oh,
it.
is that like a search engine?
Is is that AI tool, ChatGPT? It's
Yeah, I know what it is, but do you use it as like a search engine?
search. No, you ask question and it answer.
Is it accurate? Because I know that it can be trained on data
It
that isn't is
it
it
it, it is
It
very
fixes
accurate.
most of the Python code. You just put in your Python code and tell him the problem. And
Yeah,
sometimes it tells you like what's the problem.
yeah. You have to
But
confirm its accuracy, but yeah, it's very helpful.
do you pay to for the service or no?
No, it's free.
no.
Yeah, nothing on the internet
Okay.
is paid. Yeah, I don't pay for
All
that.
right, I really need to look into that.
Yeah,
I feel so old.
yep.
So yeah, that's about all I have so far, really, as an update on where I'm
Okay.
at.
Yeah. Then Phuong, do you wanna show us your graph?
Wait, I'm trying to unshare. Sorry.
Oh, okay.
All right, it's ready.
For your context everything, she's going through exactly what we went through. Oh yeah, just learning right now.
Is she coming to UCLA next year or
No, she's in the community college.
okay?
Yeah.
You just the model to train the high entropy alloys that I already like debug it and it have a graph.
Did you have any problems when you were getting everything ready? Because I know I had a lot.
Oh, like I already learned about Python, so it's not like that difficult to debug. Yeah.
Uh-huh.
But I have like the number I copy from uh the introduction here, but the graph is not the same. I don't know like why.
Yeah, I remember the graph. It did go up and down a lot, but it actually did steadily go down to 0. So yeah, my graph looks like the one that they present.
Is it your graph is same like this?
Yeah, mine looks like that. Look, yours isn't learning. I don't know what's going on.
Yeah.
Can I check your hold on, can I did you okay, so the learning rate, is the learning rate the same as you had in the code right there?
Oh. So the graph is yeah.
Oh yeah, that's very different. It seems like you got everything done, it just said it's not learning.
Yeah, so how like do you know how to fix it?
It's been a while. Can I see your code? I'm trying to figure out. So did you? Okay, so the data obviously loaded, right? Because otherwise the graph wouldn't work.
It's like the same. Really
Yeah.
like just copy the data in here.
Mhm. It looks like how the paper was when I did it. Can I go down to the optimizer part where it's learning? Oh, okay. Wait, hold on. So I don't know if this is the problem you have, but I know that when I was making my model, if I called the model before the training loop, it would initialize before it would train every time. And it caused it to go up and down a lot and it didn't train at all. I don't know if that's what's going on here because I don't remember the code word for word. Triet, do you have anything to say on this? I'm gonna check what I have written down.
I mean, there's debugging is kind of personal, I would say. So it's hard to tell, but you can do this later because it's just debugging, and it's not a
Yeah.
computational error.
Yeah,
It's
just make
very hard
sure
to trace. Yeah. Yes.
yeah, just make sure that you have like the code word for word. Because that's what I did and it worked.
And you can fix it later. It doesn't really matter.
Yeah.
And then so the next move for you is either you do variational autoencoder, variational autoencoder, or you do the GANs model. So pick one of the two, and then you can just prepare a presentation slide about them, about it, one of the two, next week.
Each one
Yeah.
or both?
Only one, only one. Pick one.
Alright.
Yeah. All right.
Alright.
So, and then yeah, and then debug the code as you want. It doesn't really matter, frankly. It just show you how's the autoencode is applied in the paper, but that's about it.
Alright.
Okay. And then another term. Oh, my bad. Should not take that. Anyways. Yeah. So this is GANs. It's an update of my GANs presentation last time, 7 weeks ago. So last time I did neural networks, I did autoencoder. I attempted to do variation autoencoder, but Cal sent me an email and he said he want me focus on the GANs instead. So I jumped from autoencoder straight up to GANs model. And so this is the first one I do is my model. So it's not very good, but I just come up with it myself. Just look at the big picture and then I just come up with the model myself. And this is I pre-process the image. Is you have a cat image, and one cat image can represent by a high-dimensional matrix. So you have each pixel represented by the one vector right here. Then the second pixel, the third pixel, the fourth pixel, and each pixel have three values for the color. So you have this one layer here, the second layer, the third layer. And that's one image. Then I convert them into a batch, including multiple image. And this is my architecture for the generator. So originally it's only this is 14 by 14 by the way. 14 by 14 at 3 channel, and then increase to 56 by 56. And then this one is just batch normalization, which happened later on in training. Faster, a lot faster. Then I increase the dimension. Like you can see from small to bigger and bigger until this point is 224, 224 is exactly the size of the image I want. And 3 channels, so it's gonna be color. There's the architectural discriminator. So the input for the discriminator is the image, the 224, 224, and then 3 for 3 channel for color. And you can see it decrease, decrease, decrease until 773, and then I flatten it out to a dense layer. And I decrease it until 1. So this 1 neurons right here is gonna determine if it's a real image or a fake image. So here's the big example. Just move this up. Into this, it's too late. There you go. Yeah. So here's the big picture. You have a random noise. You have a random noise. You put in a generator. It generates a fake image. At the same time, you take out from the real image. Here's the real image, and you input them into the discriminator, both fake image and real image. And the discriminator is gonna say either the image is real or fake. And whoever is winning, so between the generator and discriminator, whoever is winning, the one who loses have to update itself. So if the discriminator is winning, it's correctly identify the correct image, and the generator have to update itself. And on the other hand, if the generator successfully fooled the discriminator, then the discriminator had to update itself. That's the big picture. And here's my main algorithm. So first I create a random noise. I pass it into the generator, and an output out of it. And then I also get the real image from my folder. And I create the labels for the real image, which is 1, and the fake image, which is 0. Then I train the discriminator. So I have the discriminator already. I have fake image already, which is a generated output. I have real image already. I have the label already. So I can just pass everything to the discriminator. And then after that, I freeze all the weight biases in the discriminator. Then I combine the generator, which is this part, from the noise into the image size with the discriminator, is from the image to one single decision right here. So now in this one, the discriminator variables, they're frozen already, and only the generator variables are allowed to be trained on. So at this point, I pass in the random noise originally, and I train the generator, and then it repeat and repeat and repeat. So the algorithm is when I think of it myself. So it's not from the real world. It's not from TensorFlow, anything like that. I just come up with it myself. So the result wasn't very good. I find it really tricky to um, make sure the generator and the discriminator keep up with the pace. So they cannot outperform the other too much. So like if it outperform then one just keep getting 100% accuracy, and the other one keep not getting that high accuracy, just zero accuracy. And it's a very computational heavy too, because there's a hell of a lot of neural networks. You can buy both of them, so it's double computationally expensive. This one is after 250 epics, and it's like a few hours already, so I won't try more on this. I'll just give up on this. It's going to get better. And then I go to the next one, which is the TensorFlow CNN GANs. This is I got it from, yes.
Triet, I have one question. So when you were seeing this, when you're training this, could you see the loss function? Did it converge, or was it just constantly going up and down constantly?
I print out the loss function. Yeah, I print it out on my, it does decrease, but then, so different from the other models, for the GANs model, the loss doesn't matter that much, I guess, because when you reduce the loss for the generator, let's say, then where is it? Here it is. So if you reduce the loss for generator, then it increase the loss for the discriminator, and the other way around. So I can see
Oh
it
yeah.
decrease. Yeah, I can see it decrease here and then increase over there and then decrease again. But then it doesn't really have the concept of converge, thing like that.
Yeah, no, yeah, that makes sense.
Yeah.
It's a zero-sum game, isn't it? Because when one learns, the other one loses.
Yeah. At least
But
in
isn't
my
like
model, yeah.
isn't like the ideal spot though, where they should be like
Yeah,
50-50?
yeah, that's in their model, not my model though. So this is what I come up with like from scratch, just build it up my own self. Yeah. And it didn't work out, obviously. So there is some cool trick in TensorFlow, like there's something in there. So it's not just that. So this is pre-processed image. You probably knew it already. I explained it already. You convert an image into a high-dimensional matrix. The one is low-dimensional, as long as it's the matrix, because they don't use color much. They just have one assign the values of the color. It's not a color image. And then there's a batch. But I learned one of the things I learned from them is you have to use single precision for storing these things, the image, and it's float 32 as also the same thing as single precision. And the difference between this and the regular number is that for regular number it's called double precision and it's float 64. You use 64-bit to store the number, while in this case you use float 32, which is you use 32-bit to store the number. And if you use 32-bit, you use less computational power to store the number in. So the result is that it's less precise, but then it's a lot more computationally convenient. The other thing they did is they normalized the input range, the data, into -1 to 1. And the reason they do this is that they will be able to use the 10H activation. And here's the 10H activation. For 10H, they specifically use 10H for GANs model because if you look at where it has certain nice property is symmetric, is continuous, differentiable at all points, piecewise, smooth, everything. But also the main thing is that it's at 0. You can see the gradient is very steep. Actually, it's the highest gradient at 0. So it prevents the vanishing gradient problem. When it comes down to almost 0, then it gets pushed a little bit. I'm not sure how the math worked out, but that's what they say. And also this code right here is the one that I need. I found so normally up to this point, most of the time I manually pre-process the image myself. So I create pretty much everything myself and organize them myself, create batch size, things like that. So this one though, instead of doing it all myself, I found the code for organizing the all the image data a lot more convenient. So in this case, you have a buffer size, which means that how many images they want to take from the file, and it's randomly selected the image in there. So this one is technically the size of the data technically, but then you can't pick too high because your computer is not that good. It's not a TPU. But then you don't want to pick too low because you run into the overfitting problem. This is the batch size, which is just the amount of input you add into the neural networks at a time. And this uses the TensorFlow call to do everything, just prepare everything from it. So TF data was set from tensor slice. And then this is the bioarray right here. I put it in. The shuffle of the size, so the total data and the batch size right here. So this is the one code that's going to be very convenient later when you're doing TensorFlow. This is the architecture of the generator. As you can see, the generator comes from a noise vector that increase the dimension until the image size. So in this case, the input dimension is 100. The dense layer is like 12,500-ish, and it comes from this shape 7 of 7 and 256. And we also have batch normalization. I recently watched a video about batch normalization, and it's actually pretty cool to see how it worked out. So to my understanding though, so normally for the input, it's awfully normalized. And when you normalize it on the value chain, the output is the same. So it solves a problem like the exploding value, if the value is too big, then when you normalize it, it has that infinity value to reduce to a certain number. And then also the second thing it has, I believe, is on a mathematical point of view though, is have to do the gradient descent faster. And this is the activation function. We use the leaky rectifier linear unit. And then this is the regular value rectifier linear unit. This is the leaky one. And this leaky one, they have this on the left hand, the negative side down a little bit. And that's just for capturing more value, more input, while you keeping the function very simple. Other than that, yeah, so it's just you reshape it, and then this is convolutional, and then this one is at least batch normalization. This one is activation function, and again, this one right here is convolutional, and then batch normalization, activation function, and then finally it's convolutional. This is the discriminator. So the input is going to be the image size, and the output is just either is it real image or is it a fake image. You can see again, it's just keep decreasing to 1. And in this case, they have this dropout thing, and I didn't know what it means until technically what it does is that it randomly deactivates a neuron, and by doing that, it's called regularization, by the way, when you randomly deactivate a neuron. And it's for regularization, ReLU, rectifier linear unit, also do the regularization thing because you see the flat out line.
Wait, Triet, I have a question.
Yes.
Okay, so when you had the dropouts, this might be different, but from what I understand is that when you use ReLU, sometimes some nodes don't actually ever get used.
Yeah.
And so instead of trying to compute the tiny minuscule values they end up creating, they just are dropped completely to save time. Is that correct?
Yes.
Okay, cool. Also, so this is the same model with that gave you just the white noise in response, right?
Wait, I'm sorry.
Or this is the gain model that gave you just the white noise images that were generated, right?
The white noise? What do you mean?
The gray images you showed that like didn't show anything.
Wait a minute. Hold on. Like this one,
Or next slide.
this.
Is this the model that created those?
I
No,
think
this
that's a
is,
generator, right?
yeah, this is generator created it. Yeah,
There are two models, and
it's two models.
Okay.
yeah,
Oh, so the next one was TensorFlow, CNN GANs, and then what was this one for? The one with the gray images.
Oh, this one is my model. So this my model is result into this one.
is
Okay.
this supposed to be cat or?
No, they didn't use cat, so I just
No, I mean
copied
in your
this.
gray model, like,
Oh yeah, it's
what?
supposed to be cat. Yeah,
Okay,
it wasn't cat, obviously.
You may have
yeah.
covered this. What's the difference between your model and the one you were showing just now?
The main algorithm. They use a different main algorithm.
Okay.
And
It's still a gain model though, right?
It is still against model, yeah.
Okay. I'm just making
um,
sure I'm on the right track.
I have a question. Like in your GAN model, do you use the similar architect with theirs, like with the amount of CNN and
Uh,
activation function, or?
I didn't exactly use theirs, but I do realize the batch normalization is the one that like speed up the whole thing.
And for discriminator, like the very last output, that's like a 1 or 0, right? It's like
Yeah,
either
yeah,
it's real. Okay, yeah. Okay.
yeah. This is their result. I can show you. This is that. And it's only, well, it's only 30 minutes, but we got some pretty good one again. Like 0 looks pretty good. 2 looks pretty good. 9 looks pretty good. Yeah. And then I'll probably go to this next, but I will see what Cal say on Monday. Let me get back. Anyways, where am I? Yeah, so drop off. You just drop some neuron off. And then prevent overfit, which is the good one. I never know that.
I have a question. Like for
Yes.
input dimension, is what does the 28 times 28 times 1 mean? Like the 1, like,
So yeah, instead of like a color, they only use one value for the color.
oh, for color? Oh, okay. Yeah.
Yeah.
So that's like just like one batch, right?
This is one image. This
Uh,
is the
yeah,
dimension.
but how does one image only have one color?
Yeah, I mean, either grayscale, you can just assign one value for that pixel on the scale, right?
Oh, okay. It's,
Like black and white thing. Yeah.
yeah.
Right? If it's 0, then it's let's say black, and it's 1 is white, and 0.5 is gray.
I also have a question for generator part.
Yes.
I I thought convolutional was like it's like a filter that reads image, right? But how is it used to generate image, like the convolution layers and the activation functions? I'm a little bit confused about this.
Oh yeah. This one is not exactly convolutional. It's a convolutional transpose. So
Okay.
yeah, it does the opposite of the convolutional. So it increases dimension. But then how does it learn that? So I remember when we do convolutional, you apply a filter on it.
Mm, yeah.
So I guess if you think about certain way, you're applying weight on the neurons, but in a specific way. Yes, yeah. But then use the and then they have affirmation. So, yeah. I think that is a
a-
good question. I don't exactly know
And
how to
I'm
do that.
also confused about when are you inputting your data set into the generator? Is it And like, is it part of the is it in a certain step of the architecture, or is it you start by giving it data,
You
or do
give
you,
it random noise, just random.
so the random noise is the initial input dimension, which is
100.
100? What's that stand for? Is it usually, I thought image should be like 100 times 100 times something.
It's not exactly an image. It's just a single vector. It's a dense layer. So it's just a single vector. And then I convert it, I reshape it into a image.
So it's just like a random, you just randomly create something, and but random, is it a vector? What's 100 mean? Like,
Like 100 dimension.
I mean, yeah, is it like, so it's a vector with just like 100 numbers in it.
Yes. Yeah.
Hmm,
Just random.
okay,
And I increase it to like 12,000 numbers. And then I reshape it into an image.
I see.
You know, this is loss function. It's just binary cross entropy. This is the graph for the loss function. So if the generator is getting it correctly, then it's not punished that much, even if the confidence isn't as high as 1. But if it gets it incorrectly, then the loss is really high, and this lead to a strong gradient. And for the strong gradient is to prevent the fact that one of them may never catch up with the other. So if the discriminator is too good, then the generator may not be able to never be able to catch up with it. So we want a stronger gradient to make it jump faster to catch up with the discriminator. So the loss function of discriminator, the total loss is going to be the loss for the discriminator. That's the real loss plus the fake loss. The real loss is the real image with the real label, 1. A fake loss is the fake image created by the generator, and the fake label is 0. For the generator, the loss function is calculated by the fake output, which is so this is it's a fake output is the output coming from the generator, and then this one is 1. So you want to fool the discriminator. So it would make sure that primers do the opposite of the discriminator. So it's trying to make the generated image match with 1, while in fact the fake one should be 0. And this is the main algorithm. So first you create a random noise. This 100. This is not the correct one, but yeah, it's a random noise. And then you pass it to the generator. This phase is the generator training. It doesn't make much sense right now to train a generator, but you'll see in a bit. And then you train the discriminator. Again, it doesn't make much sense to train it right now, but you will see. And once you train the discriminator, you wanna for the generator training, ideally you want this to be close to the number to the real image as possible. And for discriminator training, ideally to the real output from the real image should be 1, and the fake output from the generated image, the fake image, to be 0. Then once you have the output from the discriminator, you can calculate the loss of both the generator loss and the discriminator loss. Once you have a loss, you calculate the gradient, and then you repeat the loop. You create random noise, and you do generator training. Now this makes more sense because you have the gradient already. You can go ahead and do generator training, discriminator training because you have the gradient already. Then you repeat the loop. And that's how it works out. And then you know the result. That's the result. Yeah. Any question?
I think I remember something. Go back to your previous slide. Okay, so that graph, is that basically just a comparison between loss and then accuracy?
Uh, this one is, so if is the one is truly most one, so it's just a representation of the loss function. So if it's one, then you have zero loss function, zero for the loss value. If it's zero, then you have like infinite loss value.
Okay, so it's showing loss compared to how good it predicts something.
Yes. Yeah.
Okay, very cool.
Question, comment, concern.
Oh, this is, I don't know if this is related, but I think it's related to a previous slide you had. It has to do with accuracy. So I was thinking about implementing it on my model. What exactly does accuracy measure? Like how do you, I'm not gonna ask how you implement it, but like I know that you're showing on like I think it was a presentation you had on Monday where you were showing accuracy versus loss and how they seem to not exactly be the opposite from each other.
Let's see.
I'm sorry if that didn't make sense.
Accuracy and loss.
Yeah, weren't you like on the slide that you showed at the meeting on Monday? We're discussing your model and how you had you plotted accuracy and then you plotted loss. I wonder if I don't know if this is yours or someone else's. Do you remember that or no?
No, I don't.
Okay, never mind. Sorry.
Probably a graduate student graph or something. Yeah. Yeah. Right. 18. Right. So we would have anything. We can call it a day then. I'll see you guys on Monday.
Yeah, see
Yeah,
you there.
see you Monday. Okay.